Today, among the countless proofs of Pythagoras' theorem, we'll explore one that's built entirely on physics. But before we get there, let's take a moment to understand the deep relationship between mathematics and physics. For physicists, mathematics is a tool to explore and answer questions about the universe. For mathematicians, physics serves as an endless source of inspiration, driving the creation of new tools and ideas. But Mark Levi, a brilliant mathematician at Penn State, in his book The Mathematical Mechanic, does something remarkable. He uses the principles of physics to solve purely mathematical problems. By choosing the right physical system, some problems turn into one-liners. However, as he humorously puts it, by the law of conservation of difficulty, the challenge merely shifts from tedious algebraic manipulation to the creative task of finding the right physical system. The proof begins with a simple observation: still water, in a container with no disturbances, shall remain at rest. A system is at rest if it has no acceleration, which means the net force and the total torque on it are both zero. Now, torque measures a body's tendency to rotate about a hinge when a force is applied. It's calculated as the product of the force and the perpendicular distance from the hinge. Let's consider a right-angled triangular prism, free to rotate about one of its edges. Now, fill this prism with water. The water exerts pressure on all three sides. Since the system remains at rest, the sum of torques caused by these forces must be zero. Otherwise, we'd have created an engine that runs without fuel, violating the law of conservation of energy. Now, let's take a cross-section of the prism. The force on each side is proportional to its length. For simplicity, we'll assume the proportionality constant to be 1, just a matter of scaling the units. So, the torque on the side of length A is the product of the force and its distance from the hinge, A over 2. This torque acts in the anti-clockwise direction. Similarly, the side of length B also contributes an anti-clockwise torque. But the third side, the hypotenuse, produces a clockwise torque. For equilibrium, the total anti-clockwise torque must balance the clockwise torque. Simplifying this equation gives us the Pythagoras theorem. It's fascinating, isn't it? Just by balancing torques, we rediscovered one of geometry's most beautiful results in a single line. And if you found that exciting, you should definitely check out this video in which I derive Euler's equation, this time from the physics of circular motion. Don't forget to hit that subscribe button and join us for more exciting and interesting lessons just like this.